All right, folks. So these are going to be the walkthrough notes for our acceleration content. These are the acceleration notes. You can hopefully find these on Google Classroom. But our goal for this little video lesson, we just want to relate that acceleration is essentially going to be like this rate of change of velocity. So we'll kind of look at the mathy bits of that and just sort of get a conceptual idea of how that works out. Of course, understand how velocity and position will change with respect to different rates of acceleration. And then we are going to finally look at how we can model acceleration through position time graphs and velocity time graphs. If you're at this point, you should have already started the formative questions. There's a little video breakdown about what's going on here, but here's where our notes essentially pick up. So if we're going to define acceleration as this like rate of change of velocity, a really good way that I kind of visualize acceleration is thinking about maybe how different types of cars might accelerate. Okay, so if you're a gearhead of any kind, you would probably rank your car based on how quickly it can accelerate from 0 to 60. The key here is that every single car on the market can probably go up to 60 miles an hour. Okay, um, what makes a car more maybe unique in terms of its acceleration is how quickly can it go from 0 to 60. That's essentially what acceleration is measuring. So acceleration in a more mathy type sense is of course like a vector quantity. So remember that this has both a magnitude and a direction. And the key is that it just represents a rate of change of velocity. Okay, how quickly are we changing our speed and direction? Um, we know that in order to change your speed and direction, we have to have some sort of force that's applied, right? That's Newton's first law. If there's going to be a change in motion, we have to apply a force. So that means if we're going to have an acceleration, that means that we also have to have some sort of net force. Okay, we'll kind of look at that relationship a little more closely in the next video. But just for now, know that forces and acceleration are always going to be going in the same direction. Okay, so like I said earlier, acceleration as quickly an object speeds up, slows down, or changes directions. And you can consider this little infographic as an example. Okay, so here you'll notice we have a car that's going to be getting faster and faster over time, right? So its speedometer is whoop, going up. Okay, you'll see at time 0, it's not moving at all. A second later, it's going 15 kilometers an hour. Another second later, it's going 30 kilometers an hour. And then another second, it's going 75 kilometers an hour. So over time, it just continues to get faster and faster. And it's going to be accelerating at this rate, 15 kilometers per hour per second. So what that means is every single second, that speedometer is going up 15 kilometers per hour. Okay, so it's a rate of change over distance. Okay. So a little bit more about acceleration being a vector. Okay. Um, we have to specify acceleration in the positive or negative direction, and that of course depends on whatever we set our positive or negative directions to be. Okay. Um, we want to try and be very careful with the language here. When we say uh, a negative acceleration, that doesn't necessarily mean that your object is slowing down. A negative acceleration just means that your motion is changing in the negative direction. Okay, so if you're already going in the negative direction, let's say everything going to the left is negative. If you're going in the negative direction and you're speeding up, then your motion is changing more in the negative direction. So you can have a negative acceleration, but still be speeding up. It just depends on wherever you're setting your positive and negative ends, right? Because remember that the direction does matter. Okay. Um, we want to try and not use the term deceleration just because it's more of a colloquial term. It's not really used in physics. And what we're really interested in is when you're describing acceleration, is that you're being very specific about how the motion is changing. Okay. It's one thing to say whether something speeds up or slows down. Um, but acceleration is the key to figuring out what direction is that happening. Okay, so objects slow down when they accelerate opposite the direction they're moving, right? So if I'm going to the left and I experience a negative acceleration, that means that I'm experiencing a force to the right. Okay, it's going the opposite direction of my motion. And we'll go through a couple more examples just to kind of clear that up. And like all things in physics, we can, of course, calculate this. It is pretty straightforward, but the key here, this is where it gets kind of silly. Acceleration is a rate of a rate, right? Remember that a rate is just any change in a certain quantity over time. So like velocity is a rate because it describes a change in distance over time. Well, acceleration is a rate of a rate, right? It describes the change in velocity over time. Okay. Simply put, it's how much the velocity changes in a certain unit of time, right? How quickly something speeds up, slows down, or changes direction. It's not how much it changes. Remember, every car can go from 0 to 60. That's not a really good tell. But what we're interested in is how quickly can it go from 0 to 60? How quickly can it speed up, right? Instead of just how much does it speed up. It can be a little tricky to understand, okay, especially when you start looking at the units. Remember I said it's a rate of a rate, okay? The units for acceleration are meters per second, okay? Or another way you could say that is meters per second squared, because remember, it's the change in velocity, which is already meters per second, over time, which is in seconds. So meters per second over second. Okay, so when you're calculating acceleration, and we'll have a couple of practice problems there, you just got to figure out, well, how much did the velocity change and how quickly did that change occur? Okay, a couple of notes about what acceleration is not, right? Acceleration describes the rate of change in velocity with respect to time. Okay, how quickly an object speeds up, slows down, or changes direction. It's not the same as velocity. Okay, don't mix up acceleration and velocity. They are not the same thing. Um, a large acceleration doesn't necessarily mean that you're going fast. It just means that you're changing your velocity very, very quickly, right? A large change in velocity does not necessarily mean a very large acceleration either. Okay, remember, the change in velocity is important. Okay, that's part of this acceleration equation, but it really is in respect to how long that change takes place, right? So if I am in a car that goes from like 0 to 1,000 miles an hour, right? That's a huge change in velocity, an absurd change in velocity. But if it takes me a year to go from 0 to 100, let's say I have like an unlimited racetrack and my car speedometer is slowly moving up to 1,000 miles an hour, it doesn't matter how fast I'm going at the end. If it takes forever to do that, a very large amount of time, then my acceleration is going to be really, really small. Okay. Conversely, if you go from like, I don't know, 55 to 70, okay, but you do it really, really quickly, right? It's not a huge change in velocity, but if we're doing it in a very short period of time, that's a very large acceleration. Okay, and then think back to also what we mentioned in terms of the relationship between acceleration and force. Okay, if you're in a car that goes from 55 to 70 really quickly, imagine the force that you would experience in order to make that happen, right? It's a huge jump in acceleration, which means that there's a very large force acting on you at that time too. Okay, um, let's see, what else do we want to include here? Right, yep, acceleration depends on how quickly the velocity changes, and then an object doesn't need to be moving quickly to have a large acceleration. Okay. Now, I believe your formative has a couple of practice problems here. So we got to do two things with this situation. We're going to be using the acceleration uh, equation here, but we have a car that speeds up from 5 meters per second to 15 meters per second in a time of 2 seconds. We want to first calculate the car's acceleration. Okay, so go ahead and do that. The next thing you're going to want to do is sketch a velocity versus time graph of this car. Okay, um, and now what we've done in the past are distance time graphs, right? How far it's traveled in a certain period of time. But this time we are doing a velocity time graph. Where did the velocity start? Where did it end? And how long did it take to do that? So you're going to set up your velocity time graph with time on the x-axis, velocity on the y-axis. And then the final piece is telling, well, how does the acceleration relate to the graph? And we'll give you guys a few moments to try that. and you should be able to do the following formative, and then there's a follow-up video after that.